We talk session, and we start with Alexia, who will tell us about the Lagrangian Ceresa cycle.
Well, first of all, thank you very much for the invitation to give a talk. Yeah, I'm very keen to talk about this project. So the idea of what I'm going to do today is going to be mainly constructions. What I want to do is I want to introduce an equivalence relation on Lagrangians in a symplectic manifold. Usually I'll imagine my manifold to be compact and my Lagrangians to be closed compact, but this could be generalized. So I'll call this equivalence relation algebraic Lagrangian cobordism. And then I'll show that it's strictly weaker than Lagrangian cobordism or cylindrical Lagrangian cobordism, if you know what that means, but strictly stronger than homological equivalence. And actually, this first part here is quite easy. It will be quite straightforward. And the second part requires a little bit more work and construction. And this is where the Lagrangian Ceresa cycle comes up. So the Lagrangian Ceresa cycle will be an example of a Lagrangian which is null homologous, but which is not oriented algebraically Lagrangian null cobordant. So this will be a theorem that I'll state more precisely towards the end of the talk, but I'll show the existence of such a Lagrangian. And it lives in a symplectic six-torus, which I'll also construct later in the talk. So at this point, a completely fair question would be why, and what is this equivalence relation supposed to do, and why should it be interesting? And well, it comes from algebraic geometry, is the motivation. So in algebraic geometry, you would look at algebraic cycles rather than Lagrangians. So if I take Z and Z prime to be two, say, k-dimensional cycles in an algebraic variety, say Y, then I can look at different equivalence relations between these cycles. So one equivalence relation is called rational equivalence. And I won't be very precise about these definitions, but basically this is defined in terms of families of cycles over P1. So two cycles are rationally equivalent if they're kind of fibers of some nice family of cycles over P1. And then there's a sort of weaker equivalence relation known as algebraic equivalence, which is defined in terms of families of cycles over curves. So these are curves of any genus and not just genus 0. So this is obviously weaker, and in fact, it's strictly weaker, and that's not too hard. So rational equivalence is strictly stronger than algebraic equivalence. And it's not too difficult to find examples. For instance, if you take a projective variety, because they have a lot of curves, any 2 points will have a curve passing through them. So any 2 points will be algebraically equivalent, but you can very easily find examples of projective varieties in which not every pair of points is rationally equivalent. And in turn, algebraic equivalence is strictly stronger than homological equivalence. And this is actually not so easy to come up with an example than homological equivalence. And this is what the original story of the Ceresa cycle in algebraic geometry is. So in the 80s, Ceresa constructed a cycle and showed that it was homologically trivial, but not algebraically trivial. And this was one of the first examples we had of this. Now, just to circle back to the symplectic world, Nick Sheridan and Ivan Smith have some work in which they kind of show that this rational equivalence through mirror symmetry is related in the symplectic world to what's called cylindrical Lagrangian cobordism. So if you haven't come across them, they're Lagrangian cobordisms, but instead of living over C, they live over a cylinder. And where this comes from is because the cylinder is kind of mirror to P1. But mirrors to higher genus curves are really complicated. And so it's not so obvious to think kind of what should be here, what should be mirror to algebraic equivalence. And well, probably the way I phrased the introduction, you will have guessed that this is what algebraic Lagrangian cobordism is supposed to do. So this is why, so this is kind of the motivation to try to introduce this new equivalence relation. Now, let me actually give the definition. So to give the definition, I need to tell you what a polarized tropical torus is. So B is a polarized tropical torus. The fact that it's a tropical torus just means that it's a real torus with a tropical structure. So the tropical structure is the data of a full rank lattice in the tangent bundle. So I call it TZB in the tangent bundle of B. And just by dualizing, this gives me a full rank lattice in the cotangent bundle. And polarized, I won't actually give the definition of polarization, but this means that B has a lot of tropical curves. So this is kind of a tropical abelian variety, if you will. Now, from a tropical torus, I can construct a symplectic manifold, X of B, just by taking the cotangent bundle of B with the usual symplectic structure, and then quotienting by the lattice. So this gives me a 2n-dimensional symplectic torus. And if B is polarized, this is what I call a polarized symplectic torus. And this is kind of an SYZ mirror to an abelian variety in algebraic geometry, if you're familiar with those. So, okay, now I can give the definition. So if I take two Lagrangians L and L prime in some symplectic manifold X omega, I say that they're algebraically Lagrangian cobordant if there exists a polarized symplectic torus, X of B, with 2 points, say P and Q in the base B, and a Lagrangian, say gamma, inside this product, X of B times X, and I'll reverse the symplectic form on this first factor. That satisfies the following two conditions. So the first condition, don't worry too much about it, but it's supposed to mirror the sort of flatness condition in algebraic geometry. But it tells me that if I take this gamma and I project it onto the first factor, and then I project down again onto the base here, I want this to be surjective. And the second component, the second condition is that I want sort of L to live over the point P and L prime to live over the point Q somehow. And the way to phrase this is to say that if I look at this fiber, so this here is the fiber in X of B over the point P in B, and this is a Lagrangian torus. And if I think of gamma as a Lagrangian correspondence between X of B and X, I want this to compose geometrically with F of P to give L, and gamma of FQ to be L prime. So if you're not familiar with this notation of this geometric composition, you should think of this as you take gamma, you intersect it with FQ times X, and then you can always kind of wiggle this around by some Hamiltonian isotropy to make this transverse, and then you project this down to X, roughly. So let me pause for a moment and say why this should be a good sort of symplectic mirror to algebraic equivalence, because I said that algebraic equivalence is defined in terms of families of cycles over curves, and these have very complicated mirrors. But there's an alternative picture through which you can think of algebraic equivalence as living over abelian varieties, and these have much simpler mirrors. They're these polarized symplectic tori. And so what you want is some sort of Lagrangian family over a polarized symplectic torus, and you want your L to be living above a point and L prime to be living above another point. But in the symplectic world, points are replaced by these Lagrangian tori somehow. So let me just give some examples. So the first example is if you have a cylindrical Lagrangian cobordism, that gives you an algebraic Lagrangian cobordism. So if you don't, I'm not going to give the precise definition of a cylindrical Lagrangian cobordism, but they're kind of Lagrangian cobordism that live in X times a cylinder. And if you project down onto the cylinder, what you will see is something like this. So you have L living over here and L prime living over here. And if you glue two of these together, you get an algebraic Lagrangian cobordism living over a two-dimensional polarized symplectic torus. So this is the picture. So here would have L, L, L prime, L prime. And this is an algebraic Lagrangian cobordism. You can kind of think of this as the mirror to the fact that if I have a family over P1, I can pull it back to a family over an elliptic curve by using the double cover from the elliptic curve down to P1. So a second example is if X is itself a polarized symplectic torus, then I can look at the diagonal inside this product. And this is an algebraic Lagrangian cobordism between the fiber over P and the fiber over Q for any P and Q inside in B. And this is kind of interesting to, this is interesting to compare to the cobordism case, because if P is different from Q, then FP and FQ are not, and here I need to add the word oriented, otherwise it's not true. They're not oriented Lagrangian cobordant or cylindrical Lagrangian cobordant. So these two examples are kind of already showing that algebraic Lagrangian cobordism is strictly weaker than cylindrical Lagrangian cobordism, or just Lagrangian cobordism if you prefer. So I told you that this would not be very difficult to see. It kind of follows almost immediately once you have the definition. But what would be more difficult is to show that it's strictly stronger than homological equivalence. And this is where the Lagrangian Ceresa cycle comes up. So to construct this cycle, I'm actually not going to use the original Ceresa cycle story by Ceresa, but I'm going to use a tropical version of it, which is due to Zarkov. So Zarkov considers the following tropical curve. So tropical curve is just a graph with these edge lengths. So this is my tropical curve C. And whenever I have a tropical curve, I can embed it into its tropical Jacobian. So this is a polarized tropical torus whose dimension is the genus of the curve. So in this case, this has genus 3. So this is a polarized tropical 3 torus. And it admits a group structure. And so by taking inverse for this group structure, it has a natural involution. So I call this involution phi. So I can think of C as embedded in this Jacobian. So I can think of C as living in this Jacobian. And then I can also look at the image of C by this involution. And the difference of these two is what's called the Ceresa cycle, or in this case, the tropical Ceresa cycle associated to C. And it's easy to show that this is null homologous. So it's a null homologous one cycle living inside the Jacobian, the tropical Jacobian. And then what Ceresa proves, and I'll write what Zarkov proves, but I will write Zarkov and in parentheses Ceresa, because this is the kind of tropical version of a theorem that Ceresa proved classically, is that for a generic such curve, C minus 5C is not algebraically trivial. So we want to see if there's a nice Lagrangian mirror to this story. And we've already seen that once I have a tropical torus, I can construct a symplectic manifold from this by just taking this cotangent bundle modulo the lattice construction. So if I have my Ceresa cycle living in here, the hope would be that this admits what we call a Lagrangian lift to this symplectic manifold, and it does. So I'll write this LC minus L5C. So this is a Lagrangian living in here. What does it mean that it's a Lagrangian lift? It means that if I project it down to the base, it lives almost exactly over this cycle. And I say almost exactly because really you have to thicken up the vertices a little bit. And the way you construct it is you take the union of the conormal bundles of all these edges. This gives you a piecewise linear Lagrangian, and you kind of smooth it nicely to get nice smooth Lagrangian 3 manifold in this 6-torus. And this is what you call the Lagrangian Ceresa cycle associated to the curve. And it's kind of easy to see that it's null homologous. So the theorem that you prove from here is that for generic such curve, LC minus L5C is not, and here again I need to add the word oriented algebraic Lagrangian null cobordant. So let me see. Right, I have a few minutes left. So in these few minutes, I'm going to basically explain how the proof works. So a sketch of proof. So the proof is inspired by Zarkov's proof in the tropical case. So the way that Zarkov proves that C and 5C are not algebraically equivalent is by showing that if they were algebraically equivalent, and you took a 2-chain bounding these two 1 cycles, then the integrals of differential forms on this 2-chain would have to be constrained. They would have to live in some discrete lattice. And then he explicitly constructs a 2-chain, explicitly computes an integral, and shows that generically that integral is not going to be in the lattice, and therefore they can't be algebraically equivalent. And this idea kind of transfers to the algebraic Lagrangian cobordism case, because you can show that if two Lagrangians, in this case LC and L5C, are oriented oriented algebraic Lagrangian cobordant, and you take some 4-chain bounding these two Lagrangians, then the integral over this 4-chain of omega squared has to be in the periods of omega squared. So this is some discrete lattice. And because our symplectic manifold is defined from this Jacobian here, and this Jacobian is kind of defined from the curve, the periods of omega squared, these can all be expressed. You can compute these explicitly, and they're all expressed in terms of the edge length. So these were A, B, C, D, E, and F. And now you can, from Zarkov's construction, you can kind of lift Zarkov's construction to build such a 4-chain, gamma 0, say, and show that generically the integral over gamma 0 of omega squared is not in the periods of omega squared. So this is a very rough sketch of the proof. And basically this kind of is good evidence of the fact that this definition is sort of a good mirror, not only the fact that it sits exactly where we want it to sit between homological equivalence and Lagrangian cobordism, but also the fact that this kind of famous story of the Ceresa cycle in algebraic geometry has a very nice mirror and detects something non-trivial symplectically. is very encouraging evidence that it's maybe an interesting equivalence relation to think about. Yeah, I think I'll stop here. Thank you for your attention.
Thank you. Any questions?
So I have a few questions, Alexia. First of all, thanks for your talk. Very interesting. So first question is, your cobordisms are one end to one end. Is this correct?
Yes.
Okay. So second thing, the Lagrangians that show up here, are they always embedded or sometimes they are immersed?
No, no, yeah, definitely immersed. In fact, the Lagrangian Ceresa cycle itself is immersed generally, and whenever you want to think of Lagrangian correspondence, you want to work in the immersed setting. Yeah.
Sure. Okay, great. Third question, are they obstructed or not in the sense of lower homology, or how is that?
Yeah. So, do you mean in general these algebraic Lagrangian cobordisms?
Well, in the following sense, that if you deal with a Lagrangian that might be even immersed, you can always, well, I guess you assume that they are in general position, so you have double points. Okay, yeah, not too bad. Isolated maybe, or self-transfer somehow. And then you can know if you can do floor homology with them or not. So in other words, if you can do the floor homology between one such object and another such object. And this comes down to counting some special type of curves and saying that the counts are zero or not. And
So, yes, I guess I was more wondering if you meant that in the general definition. So, if we want to get a purely symplectic definition for algebraic Lagrangian cobordism, then I think an interesting setup to work with is to require the Lagrangians to be unobstructed, and then to require that the algebraic Lagrangian cobordism itself is also unobstructed, and then to think, can I say anything Floer theoretically about these Lagrangians?
right. So this was basically what I was asking. So in part, I was asking this because a natural notion of algebraic equivalence in the symplectic world is simply to say that these things are unobstructed and are the same element in the Fukaya category. And in fact, if you have an unobstructed cobordism, this implies that they are equivalent in the Fukaya category. So basically, one can say, all right, I can replace a cobordism by, which is geometric, by an equivalence in the Fukaya category, except that this is almost equivalent in reality. So one can show that you can get an immersed Lagrangian cobordism that realizes an equivalence in the Fukaya category, in fact. And so it's very close, and so somehow this is also an algebraic notion that kind of it's probably related to what you say, but I think the key issue is what is obstructed and what is not obstructed in this story you are.
Absolutely. I mean, if you want to think of it from a mirror symmetry perspective, you're going to want your Lagrangians to be unobstructed in general. But this is a very interesting point, actually, that for Lagrangian cobordisms, you have a nice Floer theoretic interpretation of it in some way. And this is also mirrored in algebraic geometry. Like rational equivalence, you can read it off the derived category of an algebraic variety in this Grothendieck group. But I don't think, and this is something, I don't think there's a nice way that algebraic equivalence shows up. You can read it off somehow in the derived category in the algebraic setting. So it doesn't seem so obvious to find these algebraic Lagrangian cobordism groups like manifested somehow in the Fukaya category, but this is something that I find very interesting and that I want to explore and think about more.
Great, thank you. So there's more to discuss about there.
Yeah, exactly. Yeah, I have like several thoughts on this, but okay, I won't go into it too much now.
Thank you very much.
Thank you.
Okay, great. Thank you, Alexia. And maybe we'll have more questions for you in the end.